Hello and welcome to this online talk for HALG 2020. I am Themistoklis Melissourgos and I'm going to present joint work with Argyrios, Deligkas, John Fearnley and Paul Spirakis, titled Approximating the Existential Theory of the Reals, which appeared in Wine 2018. Let me start with a very well-known optimization problem, which is a global optimization of a polynomial function over a compact and convex domain. The three typical domains that have been extensively studied in the literature are the hypercube, the unit simplex, and the unit sphere under some norm, usually the Euclidean norm. Now, in this talk, we will only consider the hypercube and the unit simplex, since these are the domains that can be described by some finite vectors whose convex hull constitutes the domain. So let me start with the hypercube. Suppose that we have this polynomial function f of degree d over the hypercube. Now, what we know is that even for quadratic functions, they are at least as hard as the maximum cut problem because they can encode it. This has been shown by Goemans and Williamson and by Nesterov. And therefore, the problem is NP-hard even for degree 2. Furthermore, we know that there is no 16/17 approximation unless P equals NP, and the result is by Hastad. Therefore, we cannot hope for a polynomial time approximation scheme, since we cannot have an approximation as close to a 1 approximation as we want. Now, what about when the domain is the simplex? Then, for quadratic functions, we know that again, they can encode the maximum clique problem. This has been shown by an old paper of Motzkin and Strauss. Therefore, the problem is NP-hard. What we know further is that there is no fully polynomial time approximation scheme unless ZPP equals NP. This is again a result by Hastad. Recall that the class ZPP is the class of problems that can be solved by a randomized algorithm in polynomial expected time. So what remains after these hardness results is whether there is a polynomial time approximation scheme for degree d polynomials over the unit simplex. Here the answer is positive, and before we mention the corresponding result, let's give the definition for an approximation that we will be using. So for a given epsilon between 0 and 1, a value f prime is called an 1 minus epsilon approximation of the optimum value in the weak sense if this value of f prime is at most epsilon away from the optimum value in absolute difference. Now, a line of works by Bomza, de Klerk, and Fajbusovich, and finally by de Klerk et al., showed that for any fixed degree d polynomial over the unit simplex, there exists a polynomial time approximation scheme. And further, they showed this using an Oblivious algorithm. So let's see in a bit more detail how this algorithm works. First, they discretize the simplex into a regular grid of density k. This means that any point that we will be considering in this regular grid will have coordinates, each of which is a multiple of 1 over k. K is a natural number. So we will consider only such points, as you can see in this figure. Now, what we want to do is to evaluate polynomial f over this regular grid. As it is intuitive, as we increase the number k, so we increase the resolution of this regular grid. However, we also increase the points in this regular grid, and since we have to evaluate the function on all of these points, this makes our running time worse. So how many points are in this grid? There are p plus k minus 1, choose k, which are asymptotically p to the big O of k. And what they show in this paper is that it suffices k to be roughly t to the d plus 2 over epsilon. And then for any value f star, there exists an f prime that epsilon approximates it. Okay, and since our f star is the maximum value of f, it suffices that we evaluate overall points and we pick the highest value for f. This is guaranteed then to be at most epsilon away from the optimal value. Now we will show that the aforementioned problem is indeed a special case of a more general problem. And for this more general problem, we will provide an algorithm that hopefully gives a p-tas or a q-p-tas depending on parameters of the problem. So here is our main result informally. Instead of having one domain, we now have n domains. In each domain, we can have one vector variable. And we denote the domains by ci, and xi is the vector variable in ci. Now, each ci is determined by a set of vectors in the p-dimensional space. So for C1, L points define it. So C1 is the convex hull defined by this set of points, and so on and so forth for all n domains. Now we're also given a multi-objective optimization instance whose objectives and constraints are polynomials in our vector variables. Now suppose that the objectives and the constraints both in total are m in number. Then there is an algorithm that runs in time L plus k minus 1, choose k, to the power of n, where k is this particular number, that either outputs an n1 minus epsilon approximation, or it answers that there is no exact solution to the problem. Okay, so observe the density k that is a polynomial in n and d, and the number of objectives plus constraints m is in the logarithm in the numerator of k, and observe that in the denominator we have epsilon to the fifth. Now, here, what is true is that if there exists a solution to this problem, the multi-objective optimization problem, then our algorithm will output an 1 minus epsilon approximation of it. And therefore, if it doesn't output any answer, any approximation, then this means that the exact problem has no solution at all. So let's see how the previous problem can be formulated, can be cast into this formulation, and let's see what our algorithm gives now for that particular problem. So we consider the polynomial f of degree d over the unit simplex, and we're trying to find its maximum. So now, since we have the unit simplex, to describe it as a convex hull, we just need as many points as the number of its dimension, so p, basically. Okay, we have this unique domain, which is the unit simplex. So n equals 1. We don't have constraints. We only have one objective, and therefore m equals 1. And therefore, k is roughly d to the 6th times the logarithm of 2 times d divided by epsilon to the 5th. Now, our running time is roughly p to the big O of k. And therefore, again, this is a p-task for the problem. Now observe that in our exponent k, we have an improvement in the numerator, which is because of d, but we don't have an improvement in the denominator because it's epsilon to the 5th instead of epsilon that we had earlier. And that is because we cannot have it all. This is the price for generalizing. So let's see some properties of this main result. Again, what we do is we discretize using some regular grid of the domain with this parameter k, which we call the density. What we do is we extend a really well-known result in the algorithm game theory community, which was invented by Lipton, Markakis, and Mehta to approximate Nash equilibria. In their proof, they handle only multilinear polynomials because this is what the concentration inequalities work directly for. So for our case, we needed to make new proofs for greater than degree 1 polynomials. So again, our proof is by the probabilistic method. And as a result, it's shorter and simpler than the corresponding ones for the corresponding ones in the literature corresponding to the same results. Many well-known results from various fields are special cases of our result. And further, this theorem gives new p-tasses and q-p-tasses for some problems depending on the parameters of the problem at hand and how the parameters compare to the input size. So let me demonstrate the proof of our result by using the most easy problem, which is the quadratic optimization over the unit simplex. So suppose that we have f of x being equal to x transpose times a matrix A times x, and A without loss of generality is symmetric and normalized in 0, 1. We would like to approximate the maximum value f of x star. So for this number of k, let us construct the regular grid with density k, which consists of all samples xi from x star. X star in general can be any point within the domain. However, here we can think of it as being the one that maximizes f. Now, the following lemma is by the probabilistic method and says the following. There exists a multiset R of the regular grid with cardinality 2 over epsilon, such that for every pair of xi, xj, where xi, xj are not the same items, when this pair is applied on matrix A, then this value is at most epsilon away from the optimum value. So we can visualize these pairs xi, xj that are of different elements as the green squares in this box. Okay, these are all the ordered pairs. And observe that these are most of the total R squared squares in this box. Now, the following theorem is immediate now. The theorem says there exists a sampled vector x in this regular grid with this density, such that the value of f for this x is at most epsilon away from the optimal value. So how is this x constructed? This x is easily constructed by just averaging all the elements of set R. So then we can just evaluate this absolute difference and see the following. So x transpose times A times x is basically the sum of all the products of all pairs xi, xj divided by cardinality R squared. Okay, so let's see what this means here in this image. So we can partition these terms into two parts, one with different xi, xj, and one with identical xi, xj. So the different ones are the green squares, and the identical ones are in the diagonal. So we know that when xi, xj are different and they are applied on matrix A, then the value that they produce is at most epsilon over 2 away from the optimum. And therefore, for the green squares, the contribution is epsilon over 2. For the remaining ones, we can just bound them from above by 1, but also note that these are too few. They are R comparing with the total R squared that exists. And therefore, their contribution is just 1 over R. And because R equals 2 over epsilon, this gives the statement of the theorem. Now, also note that X is a sampled vector from the regular grid with this density, and that is because we have divided with R, cardinality R, all of the vectors in the regular grid with density K. And since K equals this number and R equals this number, then we have our new density. And this yields an algorithm with running time P to this exponent. And this is, of course, a p-tas again. Now observe that this proof is just half page long, and it's a lot simpler than the previously known ones. For p-tas is for a quadratic optimization over the unit simplex. So we know that this is a very nice framework to deal with many well-known problems. And namely, we give here some: constrained Nash equilibrium, value of Shapley games, consensus halving, standard polynomial optimization, approximate eigenvalues and eigenvectors of tensors, and computational geometry problems. Now, the interested reader can stay in the slide and check also the references. So our main result being so general, in fact, can be used to efficiently approximate an evidently hard class of problems called the existential theory of the reals. So what is the existential theory of the reals? It consists of existentially quantified formulas using the Boolean connectives. The atoms of these Boolean connectives, of this Boolean formula, are multivariate polynomial functions with rational coefficients and operators, inequalities or equalities. Now, for example, this is one such Etr formula. In general, the problem we deal with in Etr is the following: decide whether a real vector x with p coordinates exists such that the formula phi of x, the Boolean formula phi of x, is satisfied, where the Boolean formula has atoms that are polynomials compared with 0. So there is a corresponding class, computational class for existential theory of the reals. We will call this also Etr. Etr consists of the yes instances of sentences of the aforementioned form. And the input size of this problem would be the dimension size plus the size of the description of the formula. What do we know about this class? We know that it is at least as hard as NP because it can encode any satisfiability problem. And it also is at most as hard as p-space. That's because Etr can be encoded in p-space complete problem, which was shown by an old paper of Canny. In recent lines of work, there have been many problems that were shown to be Etr complete from various fields. The most interesting ones are decision versions of problems regarding Nash equilibria for more than 2 players, and some long list regarding computational complexity, computational geometry problems. So let me give you an example of an ETR problem. So we're trying to decide whether there exists an X with 3 coordinates, x1, x2, x3, such that the following formula is satisfied. So we have a set of conjunctions and then a disjunction with more conjunctions inside. So let's visualize these. So for the first set of conjunctions, we have the simplex. Okay, then for the first inequality, we have to have a solution only below the volume of this curve, and therefore within this area that is specified by this ellipse. Now, let's see what this second equality is. This is a plane, and therefore it has to be respected as well. And so the intersection of them is this line. And let's see the third equality, it's this plane. Therefore, by the intersection, we only know that this is the only feasible point that could be a solution, and in fact it is. So this red point is the solution. Now, we could have a solution also if we could satisfy the simplex and also these two inequalities, the blue and the yellow one. But these inequalities define these regions, and therefore there's no intersection between them, and the only point that could be a solution is this one. Okay. As we showed, ETR is a hard class. So what else can we do? Can we approximate it? So the approximation version asks the following: is there a vector in p dimensions that approximately satisfies the formula? For example, we have this exact formula, and we want to make an approximation version of it. So this is how we do it. We take the equivalent formula and turn all the equalities into two inequalities. And then we relax the inequalities of the formula. And we relax them by a positive epsilon in the following way. Whenever we have at least 0, we turn it into at least minus epsilon. And whenever we have at most 0, we turn it into an at most epsilon. And similarly for the strict inequalities. Okay, so what are the results on this approximate version? First, we show that if we have unconstrained epsilon ETR, meaning that the variables are not constrained, but they are free to go in all of R, then the unconstrained epsilon ETR class is identical to the ETR class. So this means that we don't need to prove at all. And this is for every positive epsilon. But this proof heavily relies on the fact that the variables are unconstrained. So what if we constrain the variables into some convex domain defined by some finite number of points? So is there an X in this convex hull that approximately satisfies the formula? So let's see again, in the previous example, where we have removed the unnecessary inequalities, let's see again how we would turn this into an approximate ETR problem. So here we have the exact problem, and we will pick some of the constraints in the formula and use them as variable constraints. So now we will use this first set of conjunctions to have as domain the simplex. So again, here we saw that the only solution is this red point. Now we will use as our domain the simplex Therefore, we will remove the first constraints from the formula, and the remaining constraints are our new formula. So now we just need to make the relaxation. The relaxation according to epsilon is like that, and now we have our approximate formula. So we need to satisfy this. And of course, this is satisfied since the exact version is satisfied. But the new feasibility region, or the new set of solutions, is this green area. And this is significantly larger than the single point set that we had in the previous version, the exact version of Etr problem. This is why intuitively, by relaxing the Etr formula, we can get a solution quickly. So, Etr problems can actually encode very hard problems from very different fields. And as we showed, all of these can be turned into an Etr formula and then relaxed by epsilon, and then using our method, we can get some Q pitases and pitases depending on the parameters of the problems. So to conclude, what's the takeaway message? The Oblivious sampling method that we develop works in all of this class. It's called function Etr, which asks for a solution of the Etr problem. This is a really vast class because it contains all of FNP and many other interesting classes. And also, the important thing here is to remember that you can formulate an approximation function problem as a constrained epsilon Etr instance, and then use our method, and you might get some pitas or q-pitas without effort at all. What are the interesting open questions? Well, motivated by problems in algorithm game theory, we present the two following. So what we have shown is that our sampling size, k, is this, roughly. But can this be improved with respect to any parameter? Well, we conjecture that the answer is yes. That is because for special cases of Etr formulas, and particularly for n-player epsilon mass equilibrium problem, we know that there are better algorithms which use a slightly different technique. And this is by Babichenko, Barman, and Peretz. So can we do the same in a more general context, though? Now, the second question is, are all of these parameters the only ones that are necessary to yield good results? Probably not, because there are some parameters that we don't take into account, such as the tensor sparsity, which is used for an algorithm, the best algorithm for two-player epsilon mass equilibrium algorithms. And the best one, by Barman, uses this sparsity parameter, which our algorithm doesn't, and which seems to be a very significant parameter for improving the running time. So that is all I have to say about the paper. Feel free to check the archive version if you have any questions. Thank you.